4 o'clock, so we shall get things started. Our speaker today joins us from Sacramento State. His educational background begins at Ohio State University with a trip through UMass and Berkeley for PhDs and postdocs. Before the talk, it's always fun to talk to the speaker to see what they work on. I was very pleased today to find out that our speaker actually has a background with Dirac monopoles, which, if you're curious, is what Sheldon Cooper and friends from the Big Bang Theory are trying to study in their trip to the Antarctic. So there's a definite real-world connection we have with our class today. So with that said, let's have a warm welcome for Michael.
I guess I should have asked to be put on that show. I didn't. So thank you for inviting me here today. This is my third CSU camp, well, fourth if you count Sacramento, which is where I come from. And they're all really nice, and hopefully maybe I'll get to all 22 at some point. Right? 22, 23, 22. Okay. But yeah, so it's been nice seeing the campus, and now I'm going to talk to you a little bit about my work that I'm doing in Sacramento, which is I'm building a low temperature lab, and I'm going to be doing some work with superfluids. So I'm going to tell you a little bit about superfluids today, and about solid helium too, and about some interesting developments that have occurred over the last 10 or so years with solid helium. So before we do that though, I just kind of want to get some background and just kind of motivate this talk about why we should study superfluids. So before I tell you what a superfluid is, I'm going to talk about why we should study them and why they're interesting to begin with. All right, so I'm going to start with this picture here. And we know that our world is very complex, right? And especially when we talk about things like the weather is a very complex thing that we want to be able to understand. And so here's two pictures of weather phenomena. So on the left here, you guys aren't so affected by this, but I grew up on the East Coast and spent a lot of time in New England. And this is what's known as a polar vortex, and it brings this bitterly cold weather to these areas. And it's got some circulating wind pattern, right, that occurs around the poles, and when it kind of comes down south, it makes it very cold in those areas. And then on the right, of course, everyone recognizes it as a hurricane, and of course, you can think that there's some circulation of the clouds or of the weather going around this central point, which is the eye, which is kind of like a singularity. And so these are very complex phenomenon, right? And as physicists, we always want to look to something simpler that we can use to maybe try and understand the stuff that's more complex. All right? And so a lot of times when we talk about flow, the easiest thing the simplest case that we can go to is these superfluids. All right? So for example, here is a picture of a superfluid. All right, and it looks remarkably similar to this hurricane, right? There is a hole in the middle, right, which is a singularity, and you can't really tell, but because the hole is here, I know that there is a flow going around that hole. So solely by having that hole there, I know that there's a flow. Right? And so, a lot of the things that are happening here are also happening in here. So maybe we could study superfluids, right, and learn something about fluid flow that'll tell us about weather as we go more and more complex. Now, I'm not going to claim that studying superfluids is going to teach you everything about the weather, right? But at least it'll start us in some model that we can use maybe to use later on down the road to understand the behavior of more complex phenomenon. All right, it's also important to study superfluids because superfluids support a lot of different topological defects, right, which come up again and again in many different areas of physics. Right, so for example, in condensed matter and solid state physics, defects come up as topological defects come up as defects in the solid, right? Which is going to be very important because that's going to be how we determine the properties of our solid. The solid properties are going to be determined by these defects. And so, for instance, we have a grain boundary, which is where you have kind of a mismatch in the lattice. All right, so a grain boundary is a planar defect. It's drawn in here as a line, but you kind of have to extend that out in 3 dimensions, and that boundary will extend out as well. So this is like a planar defect. All right, kind of one of the most important defects is a dislocation, which is a line defect. So it's a kind of mismatch in the lattice, but it's done in such a way that you have a line. The defect is along a line instead of on a plane. All right, and then we can also have point defects, where we're missing an atom in the lattice, or maybe we have an extra atom plugged in somewhere, and that would also be a defect as well. All right, so these are topological defects right? Because they have these topologies such as a plane, a line, or a point, all right, in the description of them. All right? And superfluids support these topological defects. We see them all the time in superfluids as well. So by studying superfluids, we can learn something about these defects and how they behave in solids. All right, topological defects also come up in high energy physics and particle physics. All right, and this graph is kind of pretty much all I know about high energy physics. All right, as far as I understand it, you have three of the four fundamental forces: the weak force, the electromagnetic force, and the strong force. And energy scale on the bottom, as the energy increases, you get these merging of the forces. And the way that the universe started, right, we were at a very high energy where all the forces were unified, which we call grand unified theory. And as the universe cooled, right, we start seeing these forces separate, and every time they separate, you actually get a topological defect, such as a monopole or a vortex or something, some kind of particle that's a topological defect. And so, we mentioned the Dirac monopoles. Here's a picture of a Dirac monopole in a superfluid. All right, so I'm not going to talk about this because this in itself is its own talk, but these are experimental pictures. The ones here and here are pictures of a superfluid that has a Dirac monopole inside of it. All right, and so again, even though this isn't a magnetic monopole per se, right, we can learn about Dirac monopoles, which is the basis for magnetic monopoles, which is one of the frameworks for magnetic monopoles, and maybe we can learn about how they behave because we can't see a magnetic monopole, or at least we've never seen a magnetic monopole in nature, right? So the next best thing is to make one ourselves and try and study it, right? So that's what we're trying to do here. So again, these are superfluids, right? So we can use superfluids to try and learn something that otherwise we wouldn't be able to learn, right? And finally, this is something that I just saw on, I don't remember when it was published in the archive, but there was just an article in Quantum magazine a few months ago about dark matter superfluidity. And so again, and the idea is that dark matter, I guess in some way, forms a superfluid. Don't entirely understand it at this point. I haven't had a chance to really read the paper in depth yet. But you can see these things here, right? These are vortices, right? Just like that defect that I showed you before at the hurricane, the eye of the hurricane, right? Or that center of that swirling cloud of atoms that I showed you. It's the same idea, right? So we can learn, by studying superfluids, maybe we can extrapolate that to dark matter as well, right? So we can learn study all these different kinds of phenomena simply by looking at superfluids. Right? So then where can we find superfluids? Well, many different places, all right? And some are pretty surprising as well. So kind of the granddaddy of the superfluid world is liquid helium. All right, that was where superfluid was first discovered in 1905 or 1906 or so. And so that happens when the temperature goes below about 2.14 Kelvin. You have a bucket of liquid helium, and you cool it below 2.14, 2.17 Kelvin or so, it will become a superfluid. The liquid helium itself will become a superfluid. Right? Solid helium, I'm going to talk about that. We might have superfluids in solid helium as well. All right, superconductors are really just a superfluidity of charge. All right, it's the same phenomenon, the same underlying framework. It's just charge flow instead of mass flow. All right, so superconductors are superfluids. They're just superfluidity of charge instead of mass. All right, dilute ultra-cold atomic gases, those are the pictures that I showed you. That picture of the cloud of atoms with the hole in it, that was a superfluid in a cold gas of atoms. So we took a gas of atoms, cooled it down to very low temperatures, and it became a superfluid as well. Other interesting places where superfluids have shown up are the center of neutron stars. It's been theorized that they contain superfluid as well. And this thing called superfluid vacuum theory, which again is kind of more of an astrophysical thing that I'm not entirely sure about what it does, what it means, but it has to do with vacuum theory, right, is where the particles come out when you're talking about where particles come from. They come from the vacuum, all right, and I guess that can be behaved as a superfluid as well. And then the dark matter superfluidity, which I mentioned briefly before as well. What I think is really interesting about this list, right, is that it spans, some really differing fields of physics. right? So these first three, liquid helium, solid helium, and superconductors, right, they fall in the realm of solid state physics, or what we call condensed matter physics. And these ultra cold gases, well, have the word atomic in it, so this falls into the realm of atomic physics, right? And then these applications here, right, neutron stars, superfluid vacuum theory, dark matter superfluidity, right, those are kind of astronomical, astrophysics type applications, right? So superfluids really are an important link between these seemingly very disparate fields, right? The same physics that we study for liquid helium in the condensed matter sense can help us understand maybe dark matter, right? Two very seemingly disparate fields being brought together by superfluids. And that's why I think superfluids are really interesting and fun to study, because we can do so much with them just simply by taking a vat of liquid helium and cooling it down to low temperatures. Right. So I'm going to focus in this talk mostly about liquid helium and solid helium. So I'm going to spend a fair amount of time talking about liquid helium, because that's the context where people generally think about superfluids and all the properties of superfluids. And then later on in the talk, I'm going to get into solid helium and talk about how we might be able to reconcile a superfluid in a solid as well. All right, so here's the outline for the rest of the talk. We just went through the introduction. We'll talk about liquid helium, as I said before. I'll talk about what is a superfluid, what are the properties of superfluids, what should we expect when we have a superfluid, and then at the end I'll talk a little bit about solid helium as well. All right, so let's start off. So let's talk about liquid helium. All right, I'm going to start with just a really simple idea, and that's the idea of a phase diagram. All right, so a phase diagram, it can be drawn in many different ways, right? You can have any thermodynamic property on there, right? But usually it's pressure on the vertical axis and temperature on the horizontal axis, and we have all the three common phases of matter on this chart, and we just say, all right, give me a pressure and give me a temperature, and I'll tell you what phase our material is in. Is it in the solid phase, the liquid phase, or the gas phase? And then these lines, right, those are the boundaries. So this red line is called the melting curve usually. It's the phase boundary between solid and gas, or solid and liquid. And then this blue line is sometimes usually called the vapor curve, right, which gives you the boundary between the liquid and the gas as well. All right, but the two major things that I want to point out to you on this, right, is that there's the critical point. All right, so the critical point marks the end of the vapor curve. All right. So at this point, basically, if you're kind of out here in the phase diagram, there's going to be no boundary. There's going to be no liquid-gas boundary. The liquid and the gas is just kind of mixed in together in a way. All right, and so it's only when we go down to these lower temperatures that we will start to see a phase boundary and see, all right, and the bottom is going to be the liquid and the top is going to be the gas. All right. The other point that I want to point out here is the triple point. Right, it's where the two lines, where the melting curve and the vapor curve intersect, right? And that is a place where all three phases can coexist. Right, so if you're sitting right here at the critical point, right, then you can have liquid, solid, and gas all coexisting in your system, right? So this is what I would call like a typical phase diagram. All right, here's what maybe a real one would look like, and this is the phase diagram for water. So it looks a lot more complicated than what I just showed, but it has the same basic features, right? It has, here's the phases, right? You got pressure on the vertical axis, you got temperature on the horizontal axis. Here's the gas phase, here's the liquid phase, and here's the solid phase. It just looks more complicated because there's many different phases of ice, which correspond to different orientations of the crystal. All right, and so they all have numbers, such as ice 9, which is the one that Kurt Vonnegut says is going to kill us all, right? But regardless, right there is a critical point, which is out here, and then there's a triple point right there where all three phases coexist at the same time. And so here are some critical points, just listing them for several of the first noble gases: helium, neon, argon, krypton. And then hydrogen, because hydrogen's always interesting because it's the first element, it's simple, it's easy to describe. And then nitrogen and oxygen because they're important to us. And so the critical point, remember, marks the end of the liquid gas phase boundary. So this can pretty much be considered the highest temperature at which you will have a boiling point. All right. So what I want to call out to your attention here is that helium, right, it has the lowest boiling point of any atom, right, any element. All right, that's 5.1 Kelvin. All right, so because of that, it was really the last element to be liquefied. It took until the early 1900s for them to be able to liquefy it. And then further, some really interesting properties came about. All right, so the phase boundary for helium looks like this. All right, more or less. It's a picture that I drew, so it's not exact. But this is pretty much what it looks like. All right, so again, you have your three phases, solid, liquid, and gas. All right, you have your critical point up here, right? And so that happens at 5.1 Kelvin and a pressure about 2.3 bar. All right, but the interesting thing here is that there's no triple point. Right, so there's no point on the phase diagram where all three phases coexist. All right, and as a consequence to that, all right, it means that liquid helium doesn't actually freeze under its vapor, right? So there's no point where you can have gas and solid together. All right, meaning that liquid helium will remain a liquid even if you could cool it down to absolute zero, which is 0 Kelvin. All right, so it's the only substance, the only element that will do that. All right, the only way you can solidify it is by squeezing it, by increasing its pressure, right? And then you can raise the pressure up high enough that you basically force it into a solid. Right? And I think it's worth spending a few minutes just understanding why that happens, because it's something that is kind of cool and is very accessible, I think, to students. All right, so let's spend a few minutes trying to understand why helium will not freeze at atmospheric pressures. All right, so let's do a little bit of chemistry first. All right, so there's two main isotopes for helium. There's helium-4, which has 2 protons and 2 neutrons. That's kind of pictured schematically here. And helium-3, which has 1 neutron. So it has 2 protons, so it's still helium, it just has 1 less neutron. Right? And so that's pictured down here where you have 2 protons, 1 neutron, and the two electrons. All right, but for both isotopes, so actually that seems like a small difference, right? Just 1 neutron difference. But it actually has amazingly large consequences for these 2 isotopes at low temperatures, which I'll talk about a little bit later. All right. But for both these isotopes, in either case, the neutral atom is going to have 2 electrons, which means that the first electron shell of the atom is closed. Right? And so if you're into that whole spectroscopic notation, you would say it's 1s2, right? Because there's 2 electrons, they're in the s orbital, and it's the n equals 1 state. And so basically what that means, right, is the only way that helium is going to interact is via what we call van der Waals forces. Right, so what are van der Waals forces? They're basically characterized by a long-range attraction, which is due to dipole interaction. So you have 2 atoms, right, and they kind of make dipoles out of each other. And so those dipoles will align, right, so that there's an attraction between them. All right? But if they get too close together, now the electrons start to overlap, right? The electron cloud overlaps, and so you get a repulsion because they don't want to overlap, right? So we have a long-range attraction, we have a short-range repulsion, and if we kind of draw a picture of what it might look like, it would be this. So here's this high potential energy here, right? That's your short-range repulsion. They don't want to get too close to each other. And then this kind of negative curvature here, or this negative, I guess, positive slope here. This positive slope, right, is going to kind of try and push the atoms back together. That's the attraction. All right, and so then there's some point in the middle where there's a well, where there's a bottom, right, and that's where the atoms want to be. That's the separation they want to be at. All right, and so we can approximate this curve in several ways, but one of the most popular ways, one of the easiest ways to understand is what we call the Leonard-Jones potential. For obvious reasons, sometimes it's called the 612 potential. And it's just a way of quantifying this potential between 2 neutral atoms. All right? And so in this case, here's the equation for it. This parameter epsilon is going to basically give you the depth of this well. So it's how strongly do they interact, how much attraction do they have. And this sigma gives you a measurement of the separation in equilibrium. All right, so you actually do the calculus out, you take a derivative and set it equal to 0, you actually get a 2 to the 1/6 power in there. But that sigma is basically going to characterize how far apart our atoms want to be. And so down here are just some of the parameters for several of the different noble gases again, and then I've added in hydrogen. All right, so remember, epsilon characterizes the well depth, and sigma characterizes how far apart they are. So as you see, right, helium, again, has very weak interactions, right? It's got a very small depth of the well. All right, and so those weak interactions are going to play a very important role into why helium won't freeze. Remember, because this is the equilibrium separation between the atoms. All right, but that's not the end of the story. It's not just the potential energy that these atoms have. These atoms have other energy too. And that other energy we call the zero-point motion. That comes from the uncertainty principle. All right, so you guys, as most of you hopefully know, right, from quantum mechanics, it tells us that we cannot know an atom's or any object's momentum and position to infinite precision. There's some uncertainty, right, of each of those quantities. And if we multiply those two uncertainties together, they need to equal about Planck's constant, h. Right? What that means is that even at T equals 0, so even if you're at 0 Kelvin, even if you can get that low, we still are going to have motion, right? You have to. Right? So that's a common misconception that people have, is they think that if you can cool down a system down to T equals 0 Kelvin, there's not going to be any motion. But quantum mechanics tells us that cannot be true. Right? Because if that were true, then that means that delta x, right, its uncertainty in position would go to infinity, which means that we wouldn't know where the particle is, right, which is absurd. Right? So there has to be some amount of motion still. All right? And so if there's motion, it means there's got to be energy, and we call that energy the zero-point energy. Right? And we can approximate that. All right, let's say that we have a bunch of atoms here in this square lattice. All right, this center atom here, we can say that it can live inside of this box. All right, so if the distance between atoms is r, then the length of this side is also r, right? Because this extends to 1/2 of the distance between on this side. This is 1/2 of that distance, so when you add them together, you get r. Right? So let's consider that we know that atom is somewhere inside of that box, but we don't know exactly where. It's most probably going to be in the center, right? But it could be anywhere inside of that box. All right? So that's going to be the uncertainty in position. Right? So we can use the uncertainty principle now to figure out what is its momentum going to be, what is the minimum momentum going to be if it's confined to a box of that size. All right? Well, we're just going to, instead of using r, we're going to use the volume that this atom can live in. Because remember, this is actually three-dimensional, right? So you got to kind of picture coming out at you as well. Right? So there's not just a box that it can live in, there's a volume, there's a cube that it can live inside of. Right? And so the distance r and the volume are just related, v equals r cubed, right? So r is v to the 1/3. All right, so now we can just plug that into our uncertainty principle, right? And that gives us an equation for the minimum momentum that our atom can have. And if we know the momentum, we can calculate the energy, because the energy is just p0 squared over 2m. And when we plug that in, we get this equation here for our zero-point energy. All right, so that's basically kind of like an energy of confinement. All right, we're confining our atom into that box. All right, and there's some energy cost to doing that. All right, and so we have to take this energy into account when we talk about the energy of interaction between atoms. All right, and so we're just going to add that energy in to our potential. So here's an actual graph now, done in Mathematica, so I use actual numbers here. Of the potential of helium. All right, so this is given in units of MeV on the vertical axis, and we're plotting volume, the volume that the atom can be in. So that's a molar volume on the horizontal axis. All right, but really what matters is that, right, we have our potential well, we have our long-range attraction, we have our short-range repulsion. All right, so now we're going to add in that energy of confinement, that zero-point energy from the atoms. All right, and so there it is, right? So we plug in what is the mass of helium, we plug in Planck's constant, and then we just plot that as a function of V, of volume. All right, and what you can see is that it is not insignificant, right? In fact, it is very significant. It is, in fact, greater, right, than this potential well depth. All right, so what that means is that when we add these two together, then that well is going to disappear. Right? So if that well disappears, right, there's no equilibrium position there for the atoms to sit in. They just kind of want to get as far away from each other as possible. right? And so that is the reason why helium doesn't freeze, because the zero-point energy, that energy of confinement to confine the atoms into a solid, is greater than the interaction energy, right? And so we can compare that to the next noble gas in the list, right? Neon, right? And so neon, the curves look something like this, right? So here is the blue, remember, is the interaction energy, and the red is the confinement energy. And neon has two things going for it that helium doesn't. It's got a larger mass, right? The mass of neon is larger because it has more protons in it. So it has a smaller energy of confinement, and it also has stronger interactions. Remember, helium had the weakest of the interactions, right? So it's going to have, so neon's going to have a deeper well depth. So the zero-point energy, the energy of confinement, is going to be much less significant than it was for helium. And so we see it actually has very little effect. Right? So we see that, why does helium not freeze? Right? Because of the weak interaction strength between the atoms, and because of its light mass. Right? So helium doesn't freeze, it remains a liquid. So now we cool it down, and what's going to happen is we're going to cool it down to the point where quantum mechanics is going to become important. Right? And we're going to call that a quantum liquid. All right, so how does that work? Well, again, let's return back to our uncertainty principle. All right, and we're going to actually add into the mix, along with Heisenberg, we're going to add in de Broglie. Right? And so de Broglie, remember, said that if we have a particle, we can consider it a wave as well. And that wave has a wavelength of lambda, which is given by Planck's constant divided by its momentum. Notice it's pretty much just like the uncertainty principle, right? Lambda is a length, right? So we're saying the uncertainty in that particle, in that atom, is the wavelength, right? Is the spread of its wave function. And then you have the momentum, right? So lambda times momentum, length times momentum gives you Planck's constant, right? So this is basically just Heisenberg's uncertainty principle in disguise, right? We're going to cast this in terms of energy instead. So instead of P, we're going to have the square root of 2m epsilon. All right, and we're going to compare that to sigma. Remember, sigma was a measure of the equilibrium separation between the atoms. So if you have a bunch of helium atoms, ideally they would want to be a length sigma with a factor of 2 to the 1/6 or so apart from each other. So we're going to take that wavelength lambda, that spread of the wave function of the particle, and we're going to compare it to that distance. So we're going to just take the ratio of the two. Right? And so under normal conditions, or for a kind of what you might call a normal element, this lambda is going to be a lot smaller than sigma. All right? Which means that we're going to have well-defined particles. Remember, lambda is kind of the spread of the wave function. And so what we're saying is that the spread of the wave function is smaller than the distance between particles, which means that we're going to have well-defined particles at each point. So that's kind of by this cartoon here. These dark blue spots are Gaussians that I put into Mathematica, right? So with very little wave function, with very little spread. So they don't overlap, and so because they don't overlap, we have distinct particles, right? But now we're going to cool our system down. All right, and as we do that, right, the energy is going to go down, so lambda is going to get bigger, right? That means that if lambda gets bigger, then capital lambda, right, which is just the Bohr parameter, which is our comparison, is also going to get bigger, right? And so here our wave functions of each particle have spread out, right? But the gas is the density of the atoms in here are small enough that they're not overlapping. I mean, there is some overlap down here, right? But you can still pretty much pick out a lot of the atoms there. Right? As we cool down even farther, right, eventually these are going to equal to each other, and this capital lambda, the Bohr parameter, is going to be equal to 1, right? Which means that our wave function is spread out at the order of the distance between the particles, which means we're going to start getting overlapping wave functions, all right? Which means that we're going to lose our individuality of the atoms. All right. So at this point, quantum mechanics is very important, right? Because we can't tell the atom. We don't even know where the atoms are in here. All right. All we can do is kind of describe some kind of probability of finding an atom in a certain spot. Right. And so at this point, we have now a quantum liquid. right? Because it's a liquid, but quantum mechanics has now become important, and we can't ignore it anymore. And so here are some parameters, the epsilon, sigma, and lambda for some of the different elements. And really what I just want you to point out is that for helium, for both types of helium, this de Boer parameter is much greater than well over 1, right? Which means that basically this is going to be a quantum liquid. Helium is going to form a quantum liquid. And hydrogen's on there too as well. It's a quantum liquid as well, but there are other interactions in hydrogen, right? It's not simply just van der Waals interactions, right? Okay, so let's return back to our helium phase diagram again. All right, so here it is, right? There's the solid, the liquid, the gas. There's no triple point, so there's no, so the liquid stays, so the liquid phase exists down to t equals 0. But now we know at some point we're going to hit a temperature where quantum mechanics becomes important, right? And so that happens at this line here, which is at about 2.17 Kelvin, all right, at 1 atmosphere of pressure. All right. So this is our quantum liquid phase. This is where quantum mechanics is important, and this is our what we might call a normal liquid. All right. Just historically, it's been termed. Sometimes you hear this called helium-1 because it's the normal fluid is the first phase of liquid helium, I suppose. And then the superfluid, which was this, for a while, this mystery phase when it was first discovered, was this called helium-2, or liquid helium-2. But it turned out this liquid helium-2 is superfluid. All right, so what happens is we've cooled down our helium, our liquid helium, down to a cold enough temperature that quantum mechanics is important, and the manifestation of that is superfluidity. All right. So now I've talked a lot about superfluid, but I haven't actually told you what a superfluid is or how it should behave. All right, so let's spend some time now trying to understand how a superfluid should behave. What makes a fluid a superfluid? All right, so let's talk about first what is a fluid. All right, what makes something a fluid? Well, I think there's two properties that make something a fluid. First of all, it has very little resistance to deformations, specifically shear deformations. Right, you can shear a liquid and without really any trouble, hardly any trouble. Right, and also a liquid has an ability to flow, right? And so those are kind of the qualitative measurements of what a liquid should be. We quantify that with what we call the viscosity, which is kind of its resistance to flow or its resistance to shearing, all right, to deforming. So something with a very high viscosity, think like honey, right, or molasses, right? It kind of oozes along, right? It moves very slowly. There's a very high resistance to flow. Right, and then water would have much lower viscosity because it can flow a lot easier. Right? So that's what I would call a fluid. All right? A superfluid basically just has super extraordinary fluidic properties, right? And what does that mean quantitatively? It means that the viscosity is 0. All right? It doesn't mean low viscosity, it means that there is no viscosity. All right, so it's very similar to with a superconductor. In fact, this is where they kind of come together. Right, with a superconductor, the resistance of a superconductor is exactly 0. Right, it's not that it's small; it's that it is 0. There is no resistance to charge flow. Right? A superfluid is the same, right, with just mass flow. Right, so it has a viscosity of 0, not low, exactly 0. Right, and this leads to some really interesting properties. All right, but first let's talk about how cold is a superfluid. All right, so I have this temperature scale here. All right, notice the first thing to notice is a log scale. Right, so each big line here is a factor of 10 colder than the one before it. Right, so this is 1,000 Kelvin. This is 100 Kelvin. This is the Kelvin scale. So I'm just kind of trying to give you a sense of where the Kelvin scale stands, because pretty much everything. When you talk about low temperature physics, is measured in Kelvin. So we live kind of up in this region. So a hot day in Sacramento is kind of the hottest thing I can imagine. I guess it gets pretty hot here as well too. And I believed it was very hot until I went to Chico, and they told me no, it's a lot hotter in Chico than it gets in Sacramento. But I couldn't imagine really living much above 106 or 7 degrees. And that turns out to be about 300 or a little over 300 Kelvin. Right. The coldest thing I could possibly imagine experience is a cold day in New England, and that that happens, maybe about 250 or so Kelvin, right? So all of our experiences in temperature live in just this little range here, right? We can't live much outside of this range, right? And so then we just start going down the scale, right? Oxygen liquefies, I guess it's about 90 Kelvin or so. Nitrogen liquefies at 77 Kelvin, so nitrogen, right, is most of the air we breathe. So at 77 Kelvin, that will liquefy. It will then freeze at, about 50 Kelvin. Hydrogen will liquefy at 10 Kelvin. And then helium, right, which is the lowest boiling point, liquefies at about 4 or 5 Kelvin, right? So that's down here, right? So this is the temperature scales we're talking. We're talking about temperature scales down here. Right? And then superfluid occurs down about 2.2 Kelvin or so. Right? So again, everything we talk about is going to be down in this area of this temperature scale. Right? And so what are some superfluid properties? What are some really interesting, so the quantum mechanics, right, that zero viscosity gives liquid helium some really very counterintuitive properties. Right? And if you're at all interested in stuff, and I was talking with one of the students out there about this because he was looking at these the other day. Just go to YouTube and just Google superfluid, or Google if you're on YouTube. I guess it's not really Googling. Just go to YouTube and type in the search superfluids, and you'll come up with a whole bunch of videos by this guy. I think his name was Alfred Leiter. I think was his name. I think he was from Michigan State. But these videos were made in the '60s, and which gives him kind of this cool old quality to him as well. And he has this really nice voice that he narrates in. But he just has this whole set of videos showing you these superfluid properties, which is really neat because I've actually never seen them myself, except for in videos like this, because back in the 60s, when they did these experiments, they had these glass containers that they used to hold the liquid helium. They're called dewars. And now everything's done in these big contained enclosures that you can't see inside of. Right? So unless you have some old glass dewars, which actually in our department I have found some, all right, then you're not actually going to be able to see these things anymore. But luckily these videos exist on YouTube, so we can go look at it. And if this is at all interesting to you, I would encourage you to just go look at some of these because they're really neat. So I'm going to show you some of them. All right, so the first really interesting property, right, is that you get with having no viscosity is that your fluid has no resistance to flow, right? So it can flow through pretty much any crack. All right, and this is actually a property that drives low temperature physicists nuts, because if you have any small leak in your system, the helium is going to come out and it's going to ruin your experiment. Right? So we have to make things leak tight to helium as best as we can. And so to demonstrate that, let's just watch a little bit of this video. I have the sound off because we don't actually need to listen to him, but I'll just kind of narrate what's going on. So let's see. So let's get to about 1:20, it looks like. All right. So he's got this bucket. All right, and this bucket has these really small pores that normal liquid helium can't come out of. That a normal fluid can't flow out because of its viscosity. So they're very fine pores. All right, and so there's actually helium in here now, and what you're going to see is he's going to show the temperature decreasing on this gauge in a minute here, and then eventually we're going to start seeing the helium coming out of the bottom. All right, so here comes. So we're going to hit 2.17 Kelvin, which is a superfluid transition. You'll see it. We'll talk about this bubbling in a minute, and now you're going to start seeing the helium dripping out of the bottom. You can see it dripping out of the bottom there. Right? So remember, before it went through that transition, there was nothing coming out of the bottom. Right? And so now that we've got superfluid, the viscosity is so small that it can just come right out. Right? And so if we watch another minute, now he's going down to very cold temperatures. He's going to dump the bucket in and then pull it up, and you'll just see it pour out. So you'll see the bucket come out, and then you can just see that meniscus coming right down. And you can see how fast it's coming out. Right? So that's one consequence of this superfluidity. We can watch it again, I guess. All right. Another interesting effect is that the flow rate between two buckets of helium, right? If you make a chemical potential difference between it, so you try to get helium to flow, liquid helium to flow from one bucket to the other, right? In a normal fluid, that pressure difference would relax in this kind of curved manner, right? So the flow rate depends on the pressure difference, right? And as the pressure difference gets smaller, the flow rate gets smaller as well, right? In superfluids, that doesn't happen. The flow rate is constant. Any pressure difference, any chemical potential difference between those two sides, so here we have a picture of a bucket which might contain liquid helium connected by a little channel, right? We can create a pressure difference by just making a height difference between these two, right? And if this was normal liquid, then this side would go down, this side would come up, but as they got closer together, that flow rate would slow down, right? With a superfluid, that doesn't happen. It's a constant rate no matter what the pressure difference is. All right, so that's characterized by this blue curve here, right? So the height difference would decrease linearly with time until it gets to 0, and then it would just stop. All right, so it would be a constant flow rate until that pressure difference is 0. All right, and that flow rate is called the critical velocity. All right, so superfluids will flow at a critical velocity with any amount of pressure difference between them. All right, not more, not less. All right, and then another very interesting property of superfluids is that they have a very large thermal conductivity. All right, and so you saw that bubbling and that really kind of dramatic change in the liquid. We're going to look at it again, all right, and we're going to see it happen again in a little bit more detail. All right, so let's go up to about 6 minutes here. All right, so you can see we have, this is the liquid helium here, and you can see it's bubbling a lot, right? And actually bubbles pretty violently. And then he's gonna cool down that bucket of helium, and you're gonna see this dramatic change in the properties of the liquid in its boiling. So as we watch the temperature come down, and here it is. And you get this very violent boiling very suddenly, and then it just becomes very still, right? No more bubbling, right? So what's going on here? Well, it turns out, you can watch that again while I'm talking. It turns out that the thermal conductivity of liquid helium, of superfluids, is so large that you can't really get any temperature gradients in it, right? So what's bubbling, right? When water is boiling, right? What's happening is, if you have a pot of water on the stove, at the bottom it's hot, right? So it's hot enough to form a little pocket of vapor, right? That's what the bubble is. And that bubble goes up, and then it pops, and then you have evaporation, right? That's how evaporation is occurring, right? And that's because it's hotter at the bottom, right? The liquid is hotter at the bottom than it is at the top, right? But in superfluids, you can't get that temperature gradient, right? Because it's just so efficient at transporting heat, right? You can't have any temperature gradient in the liquid. So what happens, and he's kind of demonstrating the bubbling water now. What happens is you can't get bubbles, right? And evaporation can only take place from that surface, right? Because any small temperature change will quickly be distributed throughout the whole liquid. Right. And so that's a manifestation of this large thermal conductivity that liquid helium has. All right, and then finally, I remember I showed you that picture of that superfluid with a hole in it, and I said that that hole means that superfluid is rotating. That hole is actually a vortex inside of our superfluid. Right? And a vortex is what a superfluid can do to rotate. Right? It can't rotate any other way. It has to make a vortex in order to rotate. If there's no vortex, it's not rotating. Right? Because the superfluid is called irrotational. Right? Under normal circumstances, it doesn't rotate. And the only way it can rotate, let's go back here. Oh, that far. Let's see. Where do I go? Am I going the wrong way? Okay, 1 second here. I went up. I should have gone. There it is. All right. Let's get water there. Okay. The only way it can rotate is by making that vortex. So that's how I could tell you when I showed you that picture of the superfluid on the first slide, and I said that hole means that it's rotating, because that hole is a vortex. And if it has a vortex, it means that the superfluid is rotating. Right? These vortices themselves are very, very interesting to study. They're called quantized vortex lines because the circulation around them is quantized. Right? And that's a very strong, one of the very strong links that superfluids have to a whole bunch of different fields, are those quantized vortex lines. Right? But unfortunately, I don't have time to get into them. Okay. So let's talk a little bit about the hydrodynamics of a superfluid. Right? So I've been kind of talking about superfluids as it's a normal fluid, you go below the superfluid transition, and it's a superfluid. That's not entirely the case, right? Because the superfluid properties kind of grow as you get to colder temperatures. That was kind of what you saw with that bucket where the liquid helium was going through the pores, right? When he first went below the superfluid transition, it just kind of dripped out a little bit. But then when he was a lot colder, it kind of poured out, right? And that idea comes from, the explanation for that idea comes from what we call the TwoFluid Model, right? And what the TwoFluid Model tells us is that we actually have two components to our superfluid. We have a normal component, which we call rho n, and we have a superfluid component, which the density of which is rho sub s, right? And the normal component is going to carry all of our thermodynamic properties, such as the entropy and the viscosity. So even if we go below the superfluid transition, the viscosity of helium itself doesn't drop to 0. Right? But the viscosity of the superfluid component will drop to 0. Right? And it also has no entropy, so it carries no heat with it. And I'll show you proof of that in a later slide. Right? So the superfluid component, the normal component carries all the thermodynamic properties, and the superfluid component is just kind of along for the ride. Right? But the kind of one cautionary tale is that we don't actually have two separate fluids in our liquid helium. So you can't pull an atom out and say, this atom was superfluid, and this one was normal fluid. Right? It's just a convenient way we have to describe a lot of the phenomena that we see in superfluids. Right? And so we measure the superfluid component and the normal fluid component, right? And we might guess that if we did that, right at the transition temperature, almost all of our liquid helium will be normal, and there'll be very little bit that's superfluid. And then as we get to colder temperatures, the normal fluid is going to drop, and the superfluid is going to increase, and then at the very lowest temperatures, we'll have pretty much all superfluid and very little normal fluid. All right? And so one way we can measure that, one way this is measured, is a class of very important experiments called torsional oscillator experiments. All right, so what you do, or what was done by, let's see, I don't have the name of here, the guy's name that first did this name was Androkashvili, he was a Russian physicist. He took basically a torsion rod, so a torsion rod is a rod that can twist back and forth, and he hung these spacers off of them, right? So you can imagine that the mass of those spacers is going to affect the period of the oscillations of this torsional oscillator. All right? And these spacers are very close together. All right? And they're close enough that when you put them into liquid helium, if this is normal liquid helium, then the viscosity of the normal helium will make it move along with the torsional oscillator. Right? And so the mass of the helium that's getting dragged along with the torsional oscillator will also play a role in the period in determining the period of that oscillator. Right? But if they're superfluid, right, because the superfluid has no viscosity, it's not going to move along the torsional oscillator. Right? So as we cool our liquid helium below the superfluid transition, we will see mass decouple from our oscillator. So it's not going to be affecting our oscillator anymore. So the period's going to change. All right? And if the mass decreases, if the amount of mass decreases, we will see the period decrease as well. All right? Meaning that the frequency is going to increase. And this is going to give us a measurement of the normal component and the superfluid component. So this experiment was done, And well, that's where these curves actually came from, is from doing this experiment. And this experiment is going to be very important when I start talking about solid helium as well, so remember this. All right. Another very interesting effect of superfluids is what's called the thermomechanical effect. All right, and so the thermomechanical effect is another very unique property of superfluids, and it's that the pressure difference and temperature difference are kind of come together. All right, so one way to think about it is that if you have a pressure difference, you will have a temperature difference as well. And so if you have these two vats of liquid helium, and they're separated by a superleak now. All right, so it means a superleak means that it's these pores that only a superfluid can travel through. All right, if we heat up, say, this side of the bucket, then superfluid will flow into here, and I'll show you why that happens in a minute, and it'll actually create this height difference. Well, this height difference means that there's going to be a pressure difference as well. All right, so we can actually create pressure differences simply by changing the temperature of these two sides. All right, but it works in reverse as well. If you make a pressure difference, you will get a temperature difference between these two. And it's because, how do you get a pressure difference? Well, you have to move mass from one side to the other. The only thing that will move through here is superfluid. All right, and so remember, the superfluid doesn't carry any entropy with it. Right, so you're going to get a temperature difference. All right, and this is called the thermomechanical effect. And it can be seen dramatically by another effect called the fountain effect. It's kind of the same thing, but sometimes it's called the fountain effect, where you can actually get the helium to squirt out the top of the bucket by making the temperature high enough on one side. All right, and so here is one more video of this. Let's see, so we're going to fast forward to 1:10. All right, so he's got this. These are the two buckets that are kind of stacked on top of each other. He's going to heat up down here, and it's going to draw superfluid in. There's a super leak in here, and you'll see this light shining on here. And you see the level is going up because superfluid is coming up into here because he's heating it up. All right. So he's drawing superfluid out, and you can see you can get that's a pretty substantial pressure difference, right? And the interesting thing here, let's see if I can find it. Is now he's going to do it again with a different type, with kind of a different tube, but it's the same idea. There's a super leak in that U tube, and you can see the helium spurting out the top, not a small amount, right? It's really coming out the top of that thing. Quite impressive, huh? Right, that's all in terms of, right, you're just drawing superfluid in by heating it up, and it's a pressure difference is high enough that it's spurting out the top. Right? So this fountain effect, this thermomechanical effect, also proves that superfluid doesn't carry any entropy. All right, because let's go back and think about what's happening in terms of this graph here. All right, if we're heating up this side, all right, what's happening is we're going to be changing, right? We're changing the temperature. We're heating up the temperature, right? So we're going to have more normal fluid and less superfluid than we have on this side. Question? Oh, wow, okay. Okay, so we have more superfluid than we have normal fluid. All right, so what's going to happen is there's like an osmotic pressure difference between these two sides. All right, normal fluid can't flow through. Right, normal fluid would want to go out this way because there's more normal fluid here, but it can't. So the superfluid comes in here. All right, this is hotter. Right, so we have a fluid that's flowing towards the hotter side. Right, that can't happen by the second law of thermodynamics. So that means that the superfluid cannot carry any entropy with it. All right. Okay, and so that's the thermomechanical effect, and that shows us that the superfluid component has no entropy. Really quick, I just want to talk about the background, because I think it's really interesting that superfluidity and quantum mechanics kind of grew up together. Now, I'm not saying that quantum mechanics was formulated to describe superfluidity, right, but really, in a sense, superfluidity was really the first test of quantum mechanics. I mean, quantum mechanics is designed to, was originally built up to describe light, right, and the black body radiation spectrum, right? But it turned out that it could be used to describe more. right? And that was, and superfluidity was kind of the first test of this because they really kind of grew up together, right? And if you're at all interested in the history of low temperature physics, it's a really great book. It's called The Quest for Absolute Zero. And I would suggest you go check it out because it talks a lot about this correlation between quantum mechanics and superfluidity. All right, a lot of interesting stories, a lot of interesting characters. All right, so let's get to the last part of this talk, which we're going to talk about solid helium. All right, and the question that I want to answer is, we now know that we can have superfluids in liquid helium. All right, we can have superfluids in gases, right? Because I showed you those pictures that I showed you before on the first slide with the hurricane. That was superfluid in a gas. All right, so the obvious question at this point might be, can a superfluid occur in a solid as well? All right, and so what does that even mean? Okay, well, a lot of times it's called a super solid. I think that's a little bit of a misnomer because it doesn't have super solidic properties. It's not like, it's not more solid than any other system. All right, but that's just super solid is the term that gets the funding, so that's what they use. But what is it? Well, it's a crystalline structure, a solid, mixed in with superfluid-like properties. All right, so I hope that should kind of disturb you a little bit, right? Because how can you have both crystalline order and superfluid-like properties, right? And so how can they exist together? Where should we look for supersolids? What kind of properties should a supersolid even have? And can we observe superfluidity in a solid? Right? Those are all questions that need to be answered. All right. And so, first of all, okay, let's talk briefly. How can we have a supersolid, a superfluid in a solid? Well, a classical solid, right, is just a lattice of atoms, right? That's kind of what I showed here, right? And we can take out atoms from certain places, and those are called vacancies. All right, so they're lattice sites that are missing an atom. All right, and it turns out though that these vacancies can move, right? Because if an atom moves here, the vacancy is moving in the opposite direction. All right, so these vacancies can move if the atoms can move. All right. So, and that's not really possible here, right? Because these atoms are well localized. There's a lot of energy it takes to get it to hop over to another site. All right. But a quantum solid, just like a quantum liquid, right, is going to be one where the wave functions of the atoms are going to overlap, right? So we're not going to have really as well-defined lattice sites as we like, and it means that atoms can really easily move between lattice sites. All right, so if we take out the atoms to make a vacancy, all right, well now we have this kind of smeared out vacancy, right? So if we have enough of these vacancies at low enough temperature, then we'll have that kind of quantum liquid scenario, and we can have superfluidity inside of a solid, just like we had superfluidity in our liquid, all right? And so that actually doesn't happen, unfortunately, in helium. And that's because those vacancies are thermally activated, which means it takes some energy to make them. And it turns out that you can't get enough vacancies at low enough temperature to make a superfluid. All right. So there are other possibilities which all involve defects in the solid. All right. So I'm not going to get into too much detail about them, but these vacancies, or these defects, can be a mechanism for having superfluidity in a solid. All right, so that's how we can have a supersolid. Where should we look for them? All right, what properties should they have? Should we look for a sound mode? Should we look for rotation? Should we look for some kind of hydrodynamics? All right, we're going to focus on flow of the solid. All right, and we can look at a torsional oscillator, right, which is what I showed you before, or we can look directly for flow somehow. All right, so I apologize, I'm probably a little bit rushed at this point. Took me a little longer this time than the last time. So anyway, we're going to do the same experiment that we did, only we're going to fill it out with solid helium instead of liquid helium. All right. So we had a torsional oscillator filled with solid helium, and this experiment was done in 2004 at Penn State, and they saw this clear shift in the resonant frequency, the resonant period of this torsional oscillator, and they said, aha, there's mass decoupling from this torsional oscillator. That means that there's superfluid in here. All right. Unfortunately, a lot of new data has kind of thrown this into question, but at least it funded my PhD thesis. So it was good in that sense. But another way to do it, right, is to try and push atoms through the solid. Or push the solid through some kind of small pores, right, like a super leak. Well, that was tried several times, and again, no one ever saw a signal. All right? So at this point, people are thinking, well, maybe super solidity doesn't exist. All right, but there's a third alternative, and that's, let's say we can have solid, and we try and push helium, we try and push atoms through the solid. So instead of trying to push the solid, we try to push atoms through the solid. All right, and in fact, that was my PhD thesis. And so what we see, right, so these are the pressures of these two sides here, and we see a clear relaxation between the two sides, which means mass had to have moved through that solid. All right, so that's a clear signal, right, that there is something going on in the solid, that we are able to move mass through the solid, and, right, it's linear in time, right, that relaxation is linear in time, which is what you might expect for a superfluid. Right. So, we're pretty much at the end now, and so, you know, yeah, maybe we can have superfluidity in a solid, right? But of course, there's a lot more work that we have to do to conclusively prove that. And I just want to leave you with the fact that there's really a lot of rich physics that occur in superfluids. And like I said, it ties a lot of fields together. And I think it's really interesting to be studying them, and I'm really happy to be doing that I have the ability to do that. And I just want to leave you with the fact that I have a Twitter page, and we have Pokemon in our lab as well.
Well, thank you very much. As we are at 5 o'clock, I will allow those students who are taking this, who've been here for extra credit, to depart as quickly and quietly as you can, and those who remain will take questions of the speaker in just a minute.
It's for Dr. Jones.
All right, so we have our first question. Scott.
Yeah, I think mine's just a fundamental physics question.
Okay.
On the critical point.
Yes.
It seemed to be that you were talking about the blurring of it if the temperature increases. At least the plots you showed tended to have it well separated in pressure, but not well separated in temperature.
Are you talking about helium?
Is that a real
The
effect?
helium phase diagram, or just
In the phase diagrams that I was seeing that had pressure and temperature,
okay.
which were several, and a couple of them were like from other places, and they stopped at the critical point in temperature, and they showed if it also happened in pressure, right? Then this
Yeah.
undefined above the above
Yes. So
C or something. If that's a thing.
the critical point marks the end of the phase boundary, right? So you no longer have a distinct phase boundary there. All right, you still have a gas phase and a liquid phase, but they're just kind of intermixed in some kind of weird way. And I don't know if have you ever done the experiment where you start, you know, in the liquid phase, and then you kind of increase the temperature, you know, above the critical point, increase the pressure, and then decrease the temperature again, and you'll see this kind of the liquid phase reappear. All right, so that's you see that phase boundary reappear as you cool it down again. And so that's just yeah, so it's just the end, right? So there's no more phase boundary at that point, right? But it doesn't mean that you lose liquid and solid phases. Is that your
No,
question?
I get that. But why is the figure such that you talk about losing that at higher T, but not losing that at higher
You do.
pressure?
You do. Oh well, because typically, let's see. So let's take a look at one of the. Let's see if I can find. Oh wow, it actually tells me the names of the slides. That's very impressive. Let's see. It was a phase diagram. So you're talking about. Oh, so why can't
You talk about that superposition at T larger than that.
Yeah, so if you wanted to go above, if you were down here in this region of the phase diagram, and you wanted to go above the critical point, you would have to go, you know, it's kind of, yeah, I see. So why can't you just, you could increase the pressure, right, up this way, and then you'd be above the critical pressure, and let's see, would you lose your phase boundary though? Well, there would be no phase boundary because you're up here. It's, yeah, well, yeah, so I guess it doesn't really, yeah, what matters is the critical point really kind of only matters if you're on the phase boundary, I think. Right, so yeah, you could go up this way, but now you're all in the liquid phase anyway. Right, so there is no phase boundary because you're completely in the liquid phase.
Got it. you're saying there's no functional difference between liquids and gas in that space.
Exactly, yeah.
And it only matters along the boundary. I
Yeah.
follow, thank you.
So we know helium has to be in the 4, and you mentioned that too. So when we talk about this superfluid, I don't remember if you really commented on the difference between the helium 3 and the 4.
Yeah, oh yeah, I made a reference to it, but never came back to it. So yeah, so let's see. Let's just go back to that slide where we had the helium. I'm going the wrong way, aren't I? Here it is. Yeah. Okay. So the main difference was just the neutrons, all right? But like, as I said, but I never came back to it, I said that helium-4 and helium-3, despite that little difference, have remarkably different properties at low temperatures. And the reason for that is because helium-4 is a boson, right? Because it has an even number of particles in the nucleus, right? It's got 2 protons and 2 neutrons. So if you count up the spins, they each have a half spin, so they have an even number of spin. Right? The spin it's not a half integer spin. Right? So this is a boson, right? Like a photon is a boson, which means that it follows Bose-Einstein statistics at low temperature. If you take a thermodynamics, you would know about that. And what it means is that all of the bosons, it's not subject to the Pauli exclusion principle. So they can all go into the same state. And that's what happens when you cool it down, is that all of the helium atoms, helium-4 atoms, will all go into the same state, into the lowest energy state. And that makes it, and we call it a Bose-Einstein condensate. And it's kind of the beginning of superfluidity in the statistical sense. Right? And I mean, there's a lot more to it than that, but you have basically, you have to have a boson to have Bose-Einstein condensation. Right? Helium-3 has only 3 nucleons, right? So it's going to have a half integer spin, right? If you add up halves, you're going to end up with, something with a 2 on the bottom in the denominator. All right, so that's a fermion. So it follows Fermi statistics, and they are subject to the Pauli exclusion principle, which means you can only have 1 fermion in each quantum state. Right? So when you cool it down, you're going to fill up all the quantum states. All right, so they can't all go into the lowest energy state, so you don't get superfluidity. Although that's not entirely true, because if you cool it down low enough, you will get superfluidity for the same reason that you get superconductivity. Right? So superconductors are flow of electrons, which are fermions, and they can form a superfluid. So helium-3 can form a superfluid, right, by making these Cooper pairs. Same idea. Is that?
So how low do you have to go?
For what? For helium-3?
Yeah.
It's in the, I think it's in the hundreds of microkelvin range. It's pretty low. So you need quite a setup, an apparatus setup to get that low. It's a dilution refrigerator with another stage of cooling below it. Yeah.
This question may be non sequitur, but I was thinking about your quantum fluid statement.
Yeah.
I was thinking, imagine if I had a ball of free floating quantum fluid.
Okay.
It's blue in color.
Okay.
And I fire a jet of quantum fluid that is yellow in color through it. Do they remain separate in color and only go green where they overlap? Or is there turbulence in there that will direct some of the particles of that fluid?
What makes them different colors?
Like this thing.
It's not magic, it's science, right? So basically you're saying, do they interact?
Yes.
If you have 2 different types of superfluids, well...
Even if we have the same one, with zero viscosity, you said it doesn't matter which particle is where in the overlapping probability part. I'm just trying to get if there's diffusion out, even in the quantum fluid.
Is there diffusion out? I'm an experimentalist, so I'm trying to think of this experimentally, what this would entail.
I'm not trying to experiment. I'm just trying to get the fundamental property of it.
I mean, what I didn't talk about was that theoretically when you describe a superfluid, you describe, instead of describing each particle with its own wave function, like single particle wave functions, we describe the superfluid as a whole with a wave function. All right? And so we call that the macroscopic wave function, or sometimes the order parameter. And that wave function has a phase associated with it, and the coherence of that phase is what gives you superfluidity. And I'm wondering if there needs to be some phase coherence between the two superfluids to get them to interact or something. Yeah. You have a question or? No, you have a question.
Would this be related to sort of the condensation of the growth of a superfluid? I mean, one part wouldn't be a superfluid, but you know, at some level, you're asking about adding one material to another. And so I'm thinking about what about the creation of the superfluid or the growth of it through cooling and...
So like you have like, you know, the superfluid's kind of growing towards it and you have a kind of mismatch in the phase, right? But what happens is what you find is that phase gradients correspond to flow, right? So if you have a phase difference in the superfluid, then that corresponds with a superflow. And it would flow, I guess, until the phases match. Because when you work through the quantum mechanics, you get the velocity has a gradient of a phase in it. And so that phase mismatch is also interesting because it's one mechanism that you might get vortex lines. That's the kind of one of the connections with kind of astrophysics, right? There's this Kibble-Zurich mechanism, which is how I guess a cosmic vortex can be made. And there's this kind of similarity in how it works with superfluids as well. So you can actually, because the flow, right, that can make, you know, that phase gradient gives you a flow, and that flow, if it's circulating, would make a vortex.
We'll have to turn the classroom over to the next class coming in, so we have a few extra questions and come up quickly at the end. Otherwise, let's thank our speaker.